Hey physics kids, Campbell here. Today we're going to talk about two things. We're going to talk about the rules for drawing electric field diagrams, and we're going to look at electric fields inside conductors. Now, yesterday, or in our previous lesson, we talked about calculating electric fields and how when we calculate an electric field, we need to know the direction of the electric field. And remember, we said that the direction of an electric field is set based off the way a positive charge would move. So that means away from positive charges and towards negative charges. So we need that for calculating. But sometimes it's helpful to visualize the whole space. And when we do that, we draw what's called an electric field diagram. An electric field diagram, it shows the electric field in all points of space, which is a vector sum of the contributions of the electric field from all the different point charges or whatever is in that space. So, for example, this would be an example of an electric field diagram. So it's like a map. Now, we need to know the rules so that you can draw these maps. The first rule is that lines will originate on a positive charge and end on a negative charge. Now, if I just have charges, isolated charges, so pretend that this little negative charge is in here, then my lines will start on the positive charge and extend out to infinity. Or if I just have this negative charge and this positive charge isn't here, then the lines will start at infinity and end on the negative charge. So this is if they're not in the space together, right? If they're in the space together, then they're both going to be contributing electric fields. So that's rule number one. Rule number two is that the number of lines that you draw has to be proportional to the magnitude of the charge. So, for example, if we look at these two electric field diagrams, they're both for like charges. Here are two like positive charges, here are two like negative charges, but you can see that the density of lines is different. So if we counted them, we'd find out that this has 1, 2, 3, 4, 5, 6 lines. And if we count this one, we're going to find out that there are 18 lines, which means that it has 3 times the magnitude of this charge. Now, the difference between these two diagrams is that these are positive and those are negative, so notice that our arrowheads are pointing away here and towards the charge here. But number of lines should reflect the magnitude of the charge. So if the charges are different in magnitude, then they should have different numbers of field lines. Rule number 3 is no two field lines can cross. They just can't. It's a vector sum of all of the electric fields at a point. And if you can imagine, if we put a bunch of charged particles in an electric field, they're all going to move in the same fashion. And so they're not going to bump into each other. They're going to move in unison with each other. Rule number 4 is the lines must come off a surface or end on a surface perpendicular to that surface. So when we looked at our charges right here, we can see that those lines are coming off perpendicular or landing on the charge perpendicular. And that's one of our rules. Rule number 5 is that the electric field lines should indicate the magnitude of the strength. So closer lines mean that the electric field is stronger. In fact, if you look at electric field diagrams like we looked at in these pages, you can see that the field lines are closer together, closer to the point charges. And they get farther away the farther you get. And that should make sense based off the strength of electric fields. If we take a look at this electric field diagram, I see I have straight lines here, so I'm not exactly sure what would produce this. Because the magnitude of the electric field is different, and I can tell that because the line density is different. Now, if I asked you about the strength of the magnetic field between B and C, you would say they were equal because the line density is the same for both B and C. But A, it's weaker because there are fewer lines, which means weaker field in around point A here. And of course, the field strength must be strongest here where the line density is greatest. All right, now when you're drawing field lines for multiple charges, the field diagram is a vector sum of all of the fields contributed by the charges, and your line should reflect that. So I have 2 point charges here, Q1 who's positive and Q2 who's negative, and I'm going to pick some points at certain distances away from the charges. So here at this point, all right, if we drew a straight line from the center of the charge out to this point in particular, I would have an electric field line that would be just like this. Now remember, the length of the vector is indicating the magnitude. So as we draw more and more field lines for specific points in space, those, as we get farther away from Q1, the length of the vector should get smaller. But again, they should always be pointing away from Q1 as if I drew a perpendicular line. And maybe that one's not so great there. If we do the same thing for Q2, right, my electric field lines would look like this. And again, they should be pointing towards the center of Q2. The actual electric field line is the vector sum of these. So we could imagine making little parallelograms for each of our points here, and then the vector sum would be what went from one corner to the other. And our resultant field would look something like this. One of the things that you'll see then, if we drew electric field lines, is that at each point, the resultant field at that point is going to be tangent to the field line that we draw on our map. So if we take a look at some multiple charges, here are 2 opposite charges. Now notice that the lines are coming off of these charges and landing on the negative charge fairly perpendicular. And as we look on the outside of the charges, you can see that the line density is much smaller, indicating the electric field out here is much less than it is here in the middle. And that should make sense, right? Because electric field is a function of distance. And if we look at the electric field any point in between, we're adding together the electric field. Whereas when we get outside of these points, we're actually subtracting the electric field from each other. Notice the arrowheads as well indicate the direction of the field in that it's away from the positive and towards the negative. Now if we look at 2 equal but like charges and we imagine what's going on with the electric field, right, if I asked you about the magnitude of the electric field directly in between these 2 charges, right, you would draw an electric field vector for this one that pointed in this direction, and then for this one, it would point in the opposite direction, and since they're equal charges directly in the middle, right, the electric field would be 0. They'd cancel each other out. Now, you'll notice that this electric field diagram reflects the fact that directly here in the middle, the electric field is 0. Now, that doesn't mean that it's 0 here, it's 0 in between these lines. It's not. But directly in the middle, it is 0. And you can see that reflected by this electric field diagram. Again, notice the lines don't cross, right? They come close to each other here, but don't ever cross your electric field lines. So here are 2 equal positive charges. What about 2 of like charges that are different in magnitude? Well, if you can imagine here, we go back to our 3 times stronger charge here and here. The electric field is going to be 0, not in the middle, but closer to the weaker charge. And you can see that because the 0 part is in this drawing is about right here in the middle of this area, because this charge is weaker, so this field will cancel out with this one when I get closer over here. And you can see that here as well. Now here are 2 unequal opposite charges, so there's no place around here where the electric field is 0. In fact, we could probably say that the electric field is 0 somewhere out at infinity. But you can see that while it may be weaker out here, it's not 0. And same thing over here. Now, another special case is parallel plates. Parallel plates are very useful. They are electrodes, they're capacitors. And the great thing about parallel plates, right, if you charge up these plates with equal but opposite charges, the charges are going to spread out, so they're an equidistant away from each other. So if we draw our electric field lines, right, we have these nice, evenly spaced electric field lines, indicating that the electric field here is very uniform. Now, as we get out towards the edges, the field bows out a little bit. So it's not uniform at the edges, but in the middle it is, and that has some great applications. Last thing I want to talk about is the electric field inside a conductor. Remember, in a conductor, the electrons are free to move around. And so if we put a charge on a conductor, the electrons are going to feel a force of repulsion from each other, and they're going to move until they feel no more force. So where the electric force, the net force, is 0. Now, what that means for a conductor is the excess charge, the farthest they can get away from each other is when they're on the surface, right? And then they're stuck. They can't get off the metal unless they're so supercharged that they can jump off. But other than that, they're going to accumulate there on the surface of the conductor. So we can look at this kind of like this little here. This is a conductor, although it kind of looks like a potato. But if they move till the net force on them is 0, and our equation for force is the charge times the electric field, if the force is 0, then the electric field has to be 0. So this is something you should write down in star. The electric field inside a conductor, a charged conductor, is always 0. Because what's happening here is the electric fields are canceling each other out for all of these charges. Now, another way we can prove this, besides using mathematical equations, is by drawing electric field lines. So let's take a look at a charged particle that we put inside a metal ring. So imagine that this is a solid metal ring that has a space in the middle, a hollow space, where we put a positive charge. Well, what's going to happen? Well, electrons, right, opposite charges, are going to accumulate on the inner surface of this metal ring. And the amount of charge here is going to be equal to, even though it doesn't look like it in this picture, but equal to, but opposite in sign, as the charge we put in the middle. And because this was a neutral conductor to begin with, the separation of charge leaves an equal but opposite charge on the surface. Now, if we draw electric field lines here, you can see that the field lines will leave our positive charge in the middle here and move to the outside, right? So they start on positive, they end on negative, so they end on the inner surface, and then they start on positive and go out to infinity. So again, with field lines, we can prove that the electric field inside this conductor is 0. Now, this has awesome applications. If you are ever out in a lightning storm, get in your car or a metal box, because you're in a conductor, right? Cars are made out of metal. So inside the electric field is 0, and that's where you're safest. If you ever get electronics shipped to you, you'll find they're in foil packs. They're in foil packs to prevent them from being damaged by electric shocks. And then, of course, we have our guy here with a big Tesla coil shocking the cage. And because he's inside a metal cage, we call those Faraday cages, he is perfectly safe from the high voltage on the outside. All right, I have a couple questions to ask you, and we'll see how you do. Question number 1. If charge A, what is the sign of charge A? Look at your electric field lines. If you said positive, you're correct. So remember that field lines always start on positive charges and end on negative. What is the ratio of the charge on QA versus the charge on QB? Well, if you said that QA is twice the magnitude of QB, you are correct. Now notice the absolute value signs, because obviously charge B is negative because the electric field lines are pointing towards it. But if you count the number of lines here, right, there are 4, and if you count the magnitude of the lines here, it's 8. So remember, electric field lines indicate the magnitude of the charge. Last question. The magnitude of E, the electric field at point X, is greater than the magnitude at point Y. True or false? The electric field at point X is actually less, right? Even though it's close to a field line, that doesn't matter. The density of field lines here is less. Well, how'd you do? I'll see you in class.